Welcome to the lecture series of hydrogeology. So today we are going to discuss the slug test for confined aquifers or confined formations. So if you remember from the previous one, we talked about the fully penetrating wells or the partially penetrating wells, and we discussed certain methods. So in this we are going to discuss those methods. Okay. So if I talk about the fully penetrating wells through an aquifer, so the two most popular analysis method which are used are Cooper, Bredhoft, Papadopoulos method 1, and the second one is Vorslev method or Vorslev method. It depends on the pronunciation. So the main thing which we are going to discuss here are that mostly, or you can say the vast majority of the slug test, when we look at related to the fully penetrating wells, they are analyzed using these two particular methods only. Okay. Obviously, this Vorslev method is more flexible, and as I mentioned in the previous lectures also, that this is one of the simplest and easiest method, and it is mostly used because it can be used for fully penetrating and partially penetrating wells. So it is kind of a little bit more recommended, you can say. But then apart from both of these methods, there is one recent method, or you can say a newer approach, which is Paris et al. Okay, this also, along with it, other authors might also be associated, therefore et al word has been used. So when you are going for the analysis of both well types, that is the fully penetrating and the partial one, so you can use this method as well. Okay, and if I have to go for just partially penetrating wells, then specifically there are CGS model and Degen method. But here in this particular lecture, specifically when we are dealing with the confined formations, when we are dealing with the fully penetrating one, I'm going to discuss these two particular methods only, because we'll discuss a numerical as well, that if you encounter, in field, or you have similar type of problem, so how you can basically reach to its solution, what are the tables involved, what are the standard values involved, along with the standard values, which formula you are going to use here. Okay, what kind of graphs you are going to use here, how is time related, how is hydraulic conductivity related, we'll discuss all these things. Okay, so let's start. So first, let's talk about Cooper, Brady-Hoft, Papadopoulos method. If you see on the right hand side, this is a well, and into which volume of water denoted by V is suddenly injected for a slug test. Now we are looking at what kind of aquifer over here. If you see from this figure also, this is a confined aquifer. Okay. Now what is happening? I'll come to all these parameters one by one, but let me just give you a glimpse of it. This is the effective radius of screen. This is the effective radius of casing. You can see H0. This is your rise in the water level, which is denoted. Then this is your HT, which is your original water level, and you can see function of T as well. So let's start. So just remember that whenever you are encountering such a situation as fully penetrating well or an open borehole, you have to go for this particular method. Okay, so now you have a slug or a known volume of water V, which is introduced into well over a short period of time, let's say for a few seconds. And because of this, what is the consequence? That the rise in water level has taken place. It has reached to its maximum height. What is that maximum height? That is H0. Now after it has retained its highest level, what will start happening? It will start declining. The water level will start declining. Now in this case, the head which is present above the original level, that is HT, is measured as a function of time. Therefore we are writing it in bracket over here if you see this side. Okay, now I think this is clear. So that means if I plot h, the function of t, divided by h naught as a function of time, okay, this h t divided by h naught, that means if I simply write h upon h naught on a arithmetic scale, okay, and time on a log scale, so I can get a graph out of it. That is correct, because I'm having two parameters and I see there is some information coming out from it. So till this point I think we are getting enough parameters over here. Okay, now whenever you are conducting this kind of methodology, so you have to keep in mind that there are certain assumptions. That includes a homogeneous formation. You have to consider that the formation you're taking is homogeneous, and Darcian flow. Now I think these terms are obviously clear to us at this point. And the introduction of the slug is instantaneous, like there is no slow pouring down and then taking out and everything. No, it's instantaneous, it's quite quick. This is the third assumption you will take. There are negligible well losses. Okay, these are negligible, and there are hydrological boundaries also in plane of formation, basically from a large distance from the well. Okay, so you're looking at hydrological boundaries also. So now when you have these assumptions, you can apply a formula which was given by Cooper, because he developed that following all these which follow the analytical solution to a model, and that was h t upon h naught is equal to the function of beta alpha. Now what is this? Because till now you were aware of just time, so that means you have got two more parameters over here. First of all, let's look at beta. This is a dimensionless time parameter. So its formula is beta is equal to hydraulic conductivity into thickness, that is the formation thickness we are looking at, into time t divided by RC square. That means I'm taking the radius of casing over here. Alright, so this is equal to, if I just take K into B, what is it? Just try to remember, hydraulic conductivity into thickness, that is your transmissivity, capital T, into small t divided by RC square. So when I'm saying Kr over here, so that means I'm taking the radial component of the hydraulic conductivity over here. Okay, and we have reached, this is your beta. Now time which you are taking, time is since the initial displacement of water in the well has taken place. Okay, now coming to alpha, this is a dimensionless again parameter, and this is a storage parameter. So alpha is equal to RS square SS divided by RC square. Now what does this mean? RS, if you remember, I told you this is your radius of screen, RC is your effective radius of casing, SS is your specific storage. So let's say if time is measured in seconds, then all other dimensions are in centimeter. So that means if I have to take T, it will be your centimeter square per second. Okay, and if I'm taking all dimensions in feet, so your transmissivity T is equal to feet square upon second. So you'll have to take care of these values. Okay, so I think till this point we are clear that for fully penetrating well, you will go for this particular method, and what this particular method takes into account, h, that is the function of time, divided by h naught, that is the maximum height, is equal to the function of dimensionless time parameter, dimensionless specific storage parameter. Okay, I think not specific storage, simply storage, because it is dependent on specific storage. So